Hi everybody, Larry Snider here. This is be the first talk that we'll give in Science Possible, and it'll be on chemistry. I decided to make this series for everyone who loves chemistry or wants to get re-involved with chemistry after your exposure as in high school, or if you're not doing so well in your high school chemistry, maybe you'll find our experiments and lessons a lot of fun. So let's just first say that I'll try and give you the amount of information you'd get in a first-year chemistry course. I'll try and structure things along that way. But we're going to do an awful lot of experimenting. And in the beginning, you won't necessarily understand everything that's going on in the reactions that we'll do in the lab. But that's okay. As we go on, we'll talk more and more about the subtleties of the experiments that we're doing and things that you can observe. So if you're taking notes and you're doing this for a homeschooling science class or to get better in chemistry in school, this is the definition that I've worked out for chemistry. If you think about chemistry, it's a very, very old science. As soon as people could mix things up and combine them to make other things, that's chemistry. All the alchemists in the Middle Ages, that's chemistry. Every recipe that was ever tried or perfected, that's all chemistry, kitchen chemistry. We've been improving substances that we find forever, either to increase their shelf life, like salting of meats and drying of things and so forth, or to improve their taste and digestibility, like cooking, or to improve their characteristics. The raw metals that we find in the earth aren't necessarily great for everything, but the alloys that we can make with them make them much, much more versatile. We can increase their strength or their ductility or what have you. So chemistry's been around for a long time. It may be responsible for some of or the bulk of the benefits that we find for modern life. If you're taking your notes, go ahead and put this definition down for chemistry. Chemistry is to study materials that we find, determine their characteristics, how they change, either changing state or how they combine with other things, or if they don't combine with other things. And we want to discuss the energy responsible or liberated or absorbed from these chemical reactions. So that's what chemistry is. We're going to study materials, substance, and we're going to discuss the energy requirements for reactions and the energy liberated from reactions. That'll be the first thing we do. Now, I'm going to say that for a lesson, on the first lesson of chemistry, discussing how chemistry came about by people trying to improve things in nature or learn about things in nature, that's important. And you could say that there are many, many branches of chemistry. That'd be another topic we could discuss on the first lecture of chemistry. So chemistry branches today are vast. There are probably hundreds, if not thousands, of branches of chemistry. If you think of organic chemistry, that's the chemistry of life. So biochemistry, that's an organic chemistry. If you think about environmental green chemistry now, very big topic. How to reduce pollutants from processes, or eliminate pollutants, or turn pollutants into benefits, use the byproducts of reactions. Or how to degrade something faster, right? Chemistry is involved with how can we take a problem chemical and degrade it, or how can we sequester it? We've got a terrible problem with carbon in our atmosphere. How can we sequester the carbon? These are all chemical problems that we can work on. So chemistry is a vast field. There are lots and lots of branches of chemistry. Anything that takes your interest in chemistry is a great possible career move, and I think chemistry has a bright future. Everyone should probably agree with that. There's analytical chemistry, where we can find something in nature and figure out what it's made of. Analytical chemistry is used quite a bit in the making of drugs. We find something in nature in the rainforest or something like that, and it turns out to be a good drug. Well, how can we synthesize that? We use analytical chemistry for that. So chemistry, we're going to have a lot of fun. I'll start today with a very simple reaction that many people have done, but we'll talk about how we should observe this reaction and what we can learn from the reaction. The reaction for today will just be the baking soda and vinegar reaction that everyone has done in grammar school. But we'll discuss it a little more in depth and talk about exactly what's going on and what some of the products of this baking soda plus vinegar, taking two things and putting them together, what some of the products of that reaction are. That will be next. Okay, so I promised that today's lab would be very simple. It would be the baking soda and vinegar lab that everyone's done. You made volcanoes in grammar school with baking soda and vinegar. We're going to talk about laboratory activities in chemistry, why we do them, and how they are to be observed, what you can learn from these things. First of all, we could learn a couple of things about baking soda and vinegar. Well, these are actually chemicals. And chemicals, everything's a chemical. If it's a thing, you can give a chemical formula for it. So these are household chemicals that you could buy. Baking soda, also called bicarbonate of soda. Its IUPAC name, and IUPAC is a chemical organization that kind of determines the naming of chemicals. I believe it's sodium hydrogen carbonate. Okay, so its chemical formula will be sodium hydrogen carbonate. We're going to talk about the symbols for the elements and how we name chemicals and so forth, but this is writing our equation first of all. We're going to take sodium hydrogen carbonate, we're going to add it to vinegar, another household chemical. By the way, sodium hydrogen carbonate is a base. It has a pH that is above 7. So all things with pHs from like 7 to 14 are bases. And all things from pH 7 to down to 0 would be acids. Okay, so this would be our base. I'll say base. I'm going to add it to vinegar. Vinegar, most of you know, is an acid. It's a specific kind of an acid. It's acetic acid. Acetic acid is actually its IUPAC name. And acetic acid is, I think, CH3COOH. I think that's it. So we have a carbon group here connected to an acetate group. That makes acetic acid. It's a mild acid, it's a weak acid. And actually, our vinegar has water in it also because it's not pure acetic acid. So I'm going to say plus H2O. We have water in our acetic acid. It's not a pure chemical when we buy a jug of vinegar. So our reaction is going to take a base, which is sodium hydrogen carbonate or baking soda, and we're going to react it with acetic acid. And we're going to add water, which has actually already been added. So our reaction is going to be sodium bicarbonate or baking soda plus vinegar or acetic acid plus water because there's water in our acid. And we're going to get some products. Now, you'll probably remember that this is the volcano kind of thing that they do in grammar school, and it bubbles quite a bit. So we are actually expecting a gas product out of this reaction. And there'll be some liquid left over in the container. So we're going to see if we can't run this experiment now, and then we'll come back to the blackboard and talk about our products of this reaction. If you're taking notes on this, which you should be, every time we do a lab, you should have a lab write-up. So start a new section in your notebook and say this is the baking soda and vinegar lab, and then write down its chemical formula, the common names for the chemicals, etc., and we'll begin to take observations. So I'll let you look at this board for a second, and I'll get set up in the lab. Alrighty, everybody, I'm going to get set in the lab. Now, my lab is very close to my classroom. I've picked an out-of-the-way corner of the house that I won't bother my wife too much in to set up a couple of lab tables and a storage area for glassware and chemicals. You can do the same thing. You don't need much for a lab. If you have an out-of-the-way place, that's great. If you don't have an out-of-the-way place, the kitchen makes a great lab. Here's some of the chemicals we're going to set out for this experiment. We have baking soda and vinegar. I've got a little scoopula there. I actually have an infrared thermometer, but you can use regular thermometers or a lab thermometer as long as we don't exceed the temperatures that those instruments are rated at. We're going to pick some glassware for this experiment. I'll pick something that we can see into, and then we'll do our reaction and make our observations. I've got my lab notebook out. I've got a magnifying glass because I don't see too well and I need to look at things closely. So we'll get set up with this experiment now. This will be the equipment that we'll probably need to get our lab started. I've got... Ooh, we need one more thing. These are safety glasses. Mine have a flip up where I can have a tinted or a non-tinted. I won't need the tinted, so I'm going to use my safety glasses in the clear mode. I'll put them on now because my vinegar, if I splashed it in my eyes, would sting. I don't have particularly dangerous chemicals here today. Nothing will stain my clothing, but that vinegar could sting my eyes, so I'm going to use my safety glasses. I won't need gloves. And I won't really need an apron because there's nothing staining. Baking soda, just got it at the store. This is sodium bicarbonate or sodium hydrogen carbonate. It's practically a pure chemical. So we'll use that as our base, and as our acid we'll use just household vinegar. I don't know the dilution of this. It says it has 5% acidity, but that's not very quantitative for our scientific purposes, but that'll be fine for what we're going to be using. There's 5% acetic acid in this container and 95% water, and that's usually by weight. So we'll use that. I have a little scoop here to scoop out some of my baking soda. I've got a thermometer so I can check the temperature and see if we get any temperature change with our reaction. I'm using a Pyrex reaction vessel that's kind of tall because I expect some foaming, and I don't want to foam out the top. And let's see what we can observe with our little experiment here today. I'll first start by decanting a couple of centimeters of the acetic acid and water into our beaker. Let's start with that. And I can take a temperature on this. And I can say it's 24.5 degrees Celsius. So this will be my starting point. I can make the observation that my acetic acid and water is essentially just a clear liquid. All right. This will be my sodium hydrogen carbonate. And I can see that that is a white powder. And I could note that in my lab manual. All right, so my starting conditions are I have a white powder as my base. And I have 24.5 degrees Celsius acetic acid and water solution. I'm just going to take a scoopful of my sodium bicarbonate and add it to the solution. And I've got quite a bit of bubbling going on. So I can say that there was a chemical reaction and that it was spontaneous. It occurred as soon as I mixed the chemicals together. I didn't actually have to do any mixing. I just, when they interacted, it happened immediately. If I look at my temperature, it's gone down a little bit. I'm at 23 degrees Celsius, so it dropped 1.5 degrees. This is a good note for me to make. That means that this was a spontaneous reaction and it absorbed energy from the environment. It got a little bit colder when this reaction started. All right. And it produced a gas, and it's still bubbling a little bit there. I can do a test on this gas to see what kind of gas it is. I expect that this particular gas is carbon dioxide. The test for carbon dioxide is that carbon dioxide gas will put out a lit splint. So I have a popsicle stick here, and I'm just going to light it on fire. Alrighty, and now if there's carbon dioxide being emitted from this reaction, it should put it out. Now this, I don't know if there's any left. Oh, it appears there is carbon dioxide left in this container. So just to make sure that wasn't a fluke, as soon as it goes in the container, the carbon dioxide gas has displaced the oxygen for the combustion in this container, and carbon dioxide is a little heavier than air, so it stays in the container, and it is putting out my splint. All right, so I'm making carbon dioxide gas. This is one of the products of this particular reaction, and let's see if it's still got enough acid to react with my sodium bicarbonate here. It's still making CO2. And that test is, we'll light a splint. Splint is burning nicely, and as soon as I put it in my container, that's CO2, the carbon dioxide gas extinguishes fires. That's why we use carbon dioxide gas in certain fire extinguishers. They extinguish fire. It displaces the oxygen and does not support combustion. Okay, so this is my reaction, and I can see now that my temperature has dropped further. Now it's 21 degrees Celsius. So I'm reacting more sodium bicarbonate, and it's still making CO2. By the way, I'm stirring with a thermometer. That's a technical no-no. the liquid in the container still is clear. It's effervescing still. Effervescing means the liberation of gas, and it appears that I still have reactable acid in my vessel here. And so far I've put in three scoops of the sodium bicarbonate, the base, and it's still making acid. Now my temperature's gone down to 20 degrees Celsius. As I react, the reaction is absorbing more energy from the environment, in this case the liquid. Let's see if I've still just got a clear liquid in the container, or if I'm starting to get some leftover sodium bicarbonate and unreacted in the bottom of the container. I'm still getting bubbles, but I do seem to have leftover. Now there's a white sludge at the bottom of my container. So I do seem to have some leftover sodium, unreacted sodium bicarbonate at the bottom of my container. Although the liquid itself is clear. So I would expect little to happen if I would put more sodium bicarbonate in, because there's already unreacted chemical. I see just a little bit of bubbles. Really no gas production to speak of. So right now, I've exceeded equilibrium here. I've got excess sodium bicarbonate in my solution, and I don't have enough acetic acid to make carbon dioxide. Now I can put some more acetic acid in, and I should get carbon dioxide again. I'm not going to put in too much because I don't want to overflow the container. But this should react with the sodium bicarbonate that's already in the bottom of the vessel and is unreacted. I almost overdid it. I almost had a laboratory spill. Again, these chemicals are not particularly harmful. And as I react this, now I'm down to 19 degrees Celsius. I keep absorbing energy. This reaction is spontaneous, but it takes energy out of the environment to make it happen. All right, now, I've got sodium bicarbonate as a precipitate at the bottom. And I've got a clear liquid in my solution here. I happen to know that in solution, I have another chemical that's been created, and that is sodium acetate. I've got sodium acetate in solution, sodium bicarbonate on the bottom of my container, and CO2 gas liberated from this particular reaction. Now, that product, that sodium acetate product, is a pretty cool chemical, and I would like to isolate that sodium acetate, but I have to get rid of some of the water to purify the sodium acetate. So what I'm going to do is I'm going to continue to react until all of the sodium bicarbonate from the bottom of this container is gone. So I'll add enough vinegar or acetic acid to completely react all of the sodium bicarbonate. And then I'm going to transfer this product to another container that's a wide container, and we'll heat it up and we'll evaporate. We'll speed up the evaporation of some water and reduce our sodium acetate to a pure chemical. So I'm still producing carbon dioxide from unreacted sodium bicarbonate. What I want to do is keep adding acetic acid until all of my unreacted sodium bicarbonate is used up, and then just add a little bit more acetic acid, so we're a little on the acid side. Still producing that CO2. Now I can tell my reaction is slowing here. My temperature's up around 20 degrees Celsius. Still producing plenty of CO2. Still getting CO2. Look at the bubbles of CO2 coming out of solution. This particular reaction, where we react sodium bicarbonate with acetic acid, first produces carbonic acid, which immediately decomposes to CO2 and water. So it's actually a two-step reaction. And of course the sodium acetate. Okay, I don't see that sodium bicarbonate on the bottom of my reaction vessel anymore. I'm going to add just a little bit more water. Acetic acid. Okay, and now I'm not really producing the CO2 that I was before. I think I've reacted to equilibrium. And I might just have a little bit of excess of acetic acid at this point. All right, so let's change vessels. I've got an interesting ceramic reaction vessel here. This thing has got a wide surface area, big surface area, and it's not tall. I don't need the height anymore because I'm really not going to be reacting anymore. Our reaction is finished. Go. Reaction is finished, and I have this set up where I can heat with this lab heater. I can heat the reacted mixture, and I can heated to the point where we boil off or steam off the water. Turn on my heat all the way and get the temperature going here. So I'm going to monitor this reaction, and really I just want the heat up high enough so that I get steam off the top. I don't want to get rid of my sodium acetate, I just want to get rid of the water, and I'm going to reduce my sodium acetate to a purer chemical. What I'm after is a very useful and fun form of sodium acetate called sodium acetate trihydride. Right now there's way too much water in here, but sodium acetate trihydride is, common name would be hot ice. This is a very interesting chemical that we can observe a very fun phase change reaction in. So I've got my finished reaction heating, and I'm going to drive off the water. Let me just get that heated for you. Well, now that I've been heating the product of our reaction, I started to get steam right about 70 degrees Celsius or so. And to tell you the truth, whenever you start getting the steam off this reaction, that's enough to drive off our water. So I could stop my heating here, although I may raise the temperature to about 80 or 85 degrees Celsius just to drive off the water a little bit faster. It depends how much time you have. If you're doing other things, you can just set this on simmer and leave it on low if you're doing it in the kitchen and so forth. We don't need to boil the solution. We just need steam off the top. We're going to drive off the water. And honestly, that's all that will be coming out of this. If you've got too much acetic acid in it, you might smell a little vinegar. But if we did it right, we're just going to have water coming off the reaction. I consumed all of the sodium bicarbonate. There was no white powdery sludge in the bottom of the reaction vessel, and I just added enough, a little extra vinegar above that. So just steam is going to be coming off this, and we want to reduce it to the point where our sodium acetate is just beginning to form a crystalline film on the surface. So I'm going to say right now I'm at 80 degrees Celsius. I'm going to say that this is the maximum temperature I want, and we'll let this go for a while. Now you're going to reduce the volume on this quite a bit. We may only end up with a quarter of the volume that we started with, and I didn't take a measurement of what we started with, but we're gonna essentially heat this down till a very, very small portion is left, and that will be our sodium acetate trihydride. Well, it's been about an hour and change since I started this, and I'm just now to the point, I want to say I'm less than a quarter of the amount of the original reagent. I'm almost down to saturated. Oh, there it is. Can you see the surface of the sodium acetate in solution? There's crystallization on the surface. I hope we can see this. There's a very thin film of crystallization forming on the surface of the sodium acetate. Now we're at saturation at this high temperature. So when I cool it down to room temperature, it'll certainly be super saturated, and this is exactly where we want it. So here's my sodium acetate. It's no longer clear. Now we've got a slight brown color to it, but we're ready to stop the heat. Got the heat done. And we're going to strain it into another vessel. Here we go. I've got it set up for decanting into a storage vessel. That's just a coffee filter and a funnel. Now you've got to be careful with your reagent right now. It's hot and it would burn you, so it's a burn hazard like any hot liquid. All right, now hopefully if there's impurities, especially particulate impurities in my reagent, they'll be filtered in the coffee filter, and we'll get a fairly clean, pure distillate. We'll notice that the color is not clear anymore. I suspect that there's some sugars in our acetic acid. That's our vinegar. So the source for vinegar is usually grape juice or some other fruit juice, and they ferment it into alcohol, and then they continue the fermentation until they get acetic acid. So I expect those sugars are responsible for our off color, but I don't think they're going to hurt our chemical. When I get this fully decanted, I will talk about our products. Well, here's the finished product. This is our sodium acetate, hopefully trihydride. There's some crystallized sodium acetate trihydride, hopefully in the bottom of our evaporation disc. I'm going to scrape this out, and when the powder is completely dry, I'll grind it in a mortar and pestle, and I'm going to save this. This is a powdered chemical that we can use to start a reaction with the sodium acetate. All right. I've got, I don't know, I might have a whole gram of sodium acetate solid. And 22 milliliters or so of sodium acetate liquid. There we go. I'll powder that and put it in a little reagent jar. So now, after our lab is finished, you can finish writing it up. We started with sodium hydrogen carbonate, that's our baking soda. We added that to liquid acetic acid and water, that is acetic acid, CH3COOH, and water, H2O. It liberated carbon dioxide gas. And we synthesized a new chemical, sodium acetate. And we also produced a little bit of water. Next time I make a video, we'll do some experimenting with our synthesized sodium acetate trihydride, and we'll have a lot of fun with that. And I will give you another lesson in chemistry. We'll start to think about substances and how to classify them and some of the characteristics. Hope you enjoyed watching this first video. Thanks a lot.